Alright, number 10 matches C. Number 12 matches D. 10, C as in...
Hey, Charlie.
Charlie, that's right. D as in Delta, right?
That's
Number 14, D as in...
Bravo.
Bravo. What's D? It's not Delta? Sorry.
No, D is Delta.
Oh, okay.
For D is Delta.
Number 22, alright, it was a graphing one. Number 22. Technically, Maddie, I do have other paint back here if you want different colors. And I have different brushes. Okay, kiddos, how would you graph cosecant? Graph sine, and then vertical asymptotes every time it hit the axis because it didn't shift, and then bouncy, bounce, 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 right? Bouncy, bounce, bounce, bounce. Number 28. Guys, do you have to be showing this table?
No.
No. What do I need you to be showing? Labeling the graph and making it clear that you're putting this point at pi over 8 and that point at 3 pi over 8. So as long as you're labeling the graph, I won't make you put it over here. Can you scroll down so that you guys don't feel like your time is being wasted?
That's not a Santa hat, by the way.
That is
Like,
a
that's like
Santa.
an elf.
Okay, cotangent. What do you guys find first? Hopefully vertical asymptotes. Hopefully vertical asymptotes. So when you found the vertical asymptotes, they should have been happening every 2, I think. Is that what you found? 2n?
Oh, yeah.
Cool. So then 2n would be 0, 2, 4, 6. You can keep on going however long you want. If you were to find your period, we didn't specifically write this. We did write the period of cotangent was pi, but if you wanted to find the period, you would have had to do 1 over b times pi, because, just pretend this is working. What, if that did not work, that's 2 pi. Okay. 1 over b times pi. Question, kiddos, why did they put a pi? Why did I put a pi? Isn't it usually 2 pi? What's the period for tangent and cotangent? Pi, yeah. So for sine and cosine and cosecant and secant, it's 2 pi over b, or 1 over b times 2 pi. Tangent and cotangent, remember, their period is pi. So we would have taken the pi over 2, we would have multiplied by the reciprocal, and that's why every 2. But if you guys followed my trick, didn't my trick say to take this guy? What are we supposed to do with that guy? Set him equal to, for our vertical asymptotes, right? Set him equal to, what were cotangent's vertical asymptotes from our notes? Half. Nope, not, that's tangent. Pi n. Pi n.
Got it.
And what would you have done to both sides? I would say probably times 2, right? You know the way. So you have pi x equals 2 pi n. How would you have solved for x?
2n.
2n. And that's why the period is every 2, and the asymptotes are at every 2. 0, 2, 4, 6. Do you need the table? Not necessarily, as long as you put your point of inflection halfway in between, halfway in between, halfway in between, at 1, at 3, at -1, at -3. And question, why is the curvature slight?
Oh, because
Because it's a vertical stretch.
yes.
Does that make sense?
That.
Good. Vertical stretch, slight curvature. Let's keep going. Oh my goodness, you were allowed to use a calculator on 40 and 48?
Yes, ma'am.
Pause those!
Am I happy with
40 would have been easy. There's a tangent button. But
48 was
wait,
hard.
wait. How would you have used your calculator for number 48?
Divide.
Divide by 1.
1 over.
Did you get it?
Yeah.
Because secant, there's no button for secant.
Yes, you have to put
But secant is 1 over cosine. We put it all in. And what's with the, okay, you could have written it 1/3 times. Couldn't you have written, Chris? Please. You could have written 1/3 times 1 over cosine. But either way, you had to put in that whole argument of secant into the cosine. You could have written them separately if you wanted. They just put it all together to make it look nice, yada, yada, yada. But then, if you're in radian mode, you should have seen the bouncy, bounce, bounce, bounce.
Yep.
Off of the cosine.
You really should make a secret.
A secant button? That'd be too easy.
Why?
Because then you'd have to have more buttons on your calculator and then have to make it bigger and then bigger is better, right?
Bigger is
Or
better,
it could have been
correct.
second, so.
Excuse me?
But it can't be second sign, because second sign we're gonna talk about today is section 4.7. Four different meanings.
Excuse me?
Pause,
I need to take like a 40-minute bathroom break.
pause. Number 56. You were supposed to take cosecant and see when it equaled. Guys, what do you see them doing? What did they graph? Who's this guy?
The graph. Oh, close.
He's bouncing off the see the sine curve underneath.
Yes.
Okay, so cosecant, they graphed cosecant. What else did they graph? Who's this guy? Let me show you. Let me show you.
What?
What did they do? This was our y1 cosecant.
What's going on?
I don't know what this is. That is our y1. This was our y2. I'll just write it outside the box.
Think outside.
That's, exactly. That's our y1, that's our y2. Kiddos, when will y1 equal y2? Graphically, how do you see them, or where do you see them equaling?
The bounce.
They are bouncing off, but when will two graphs equal each other? When they intersect. And what can you use on your graphing calculator to find intersections? Second trace, the intersect button, no big deal yet. Now, if you had used your calculator, would you have gotten nice, pretty answers with pi's and over 3's?
No, ma'am.
What would you have gotten? Decimals. So if you wrote down decimals, you're not wrong necessarily. Plug them in and see if they match up. But the decimals end up corresponding to these nice unit circle answers. But if you have decimals, just plug in like a pi over 3 and see if it matches up with one of the ones that you got. They were telling you basically graph it, look at the intersections, and ask yourselves where they happen. So you can use your calculator to help. Number 58, you were using the odd property? Oh, I don't know. That one was just like, think about tangent, PS, he's odd. We put that in our notes though, didn't we? Okay, we put that in our notes. Number 70. Number 70, I think they had you graph both and then see what was going on, and what did you guys notice? How many graphs were there, even though there were two functions? Just one. Wait a minute, if there's only one graph and you're graphing two functions, what does that mean about the two functions? They must be equal. So that is that? Yeah. Weird, but true. And then the last ones, did you guys see your damping, your waves being dampened? Now this one's kind of hard to see, but this 2 to the power of negative x squared over 4, that's that top limit. Then the flip of that would be the bottom limit. And if you guys zoomed in, guess what this guy does right here? Yeah, it goes down really quickly. It does do a little bit of the bounce right there. It keeps technically waving for a little bit, it's just so small you can't see it. But that yesterday we saw happens when one function holds in the other. And then you graph one more, 1 minus cosine of x over x, and that was another one where divided by x also dampened it, but in a very different way. Multiplying is when you have the top being bound and the bottom bounding. When you divide, it just happens a little differently. So they wanted to show you that's a thing. The snazzy thing they were asking is what's happening to the wave as you go to the right to the left? What's happening to the wave as you go to the right? It's going to 0. And this guy, what's happening to the wave as you come in towards 0? It's also going to 0. So they're having you kind of look at the graphs a little bit and see what was going on with your waves. We're almost done. 2 more? 84, I think, was a plug-in chunk. They gave you adjacent, you wanted hypotenuse, so set it equal to cosine. They had you solve for D, and this is one way of writing it, 27 over cosine. They just said, hey, guess what, that's secant. Then they had you graph it. You guys know how to graph secant, right? Just 1 over cosine. Or 27 secant, graph 27 over cosine, and then they just graphed it. You can make your x min and x max the boundaries. And last but not least, they had you answer some questions. Guys, in math, what is the little arrow talking about? Approaches. Good. approaching. So, on this one, can I just draw a tangent real fast? We have negative pi over 2. We have pi over 2. We have our tangent. Is tangent optimistic or pessimistic?
It's pessimistic.
Uh-oh. Is he looking up or looking down?
Looking up.
There you go. Some of you might not know the optimistic, pessimistic thing. Anyway. And then he keeps on looking up after the vertical asymptote. Then he keeps on looking up before the vertical asymptote. Okay. This one is trying to introduce you to some signs, some notation in higher math. As x gets closer to pi over 2, which is this guy, the plus means from numbers a little bit bigger than. From numbers just a little bit bigger than. So what that's talking about is, get your pi over 2, go just a little bit above. Where's my graph? Down. And where's he going? Down. Negative infinity is where the y's are approaching. The little minus sign in the exponent means take pi over 2, go a little bit before. Where's my graph? And where's he headed? Exactly. Negative pi over 2. The little plus sign needs to go just a little bit above. Where's my graph? And where's he headed? AKA negative infinity. Go to negative pi over 2, go a little bit below. Where's my graph? And where's he headed? Okay, that's all it's filling in. Is that okay? Sort of, kind of, maybe? Alright. So this is introducing you to some notation that does show up in like calculus and higher maths as well. The arrow is approach, and the little pluses and minuses are talking about a little bit above, a little bit below. With that, kiddos, we are done with section 4.6. We do need to get into 4.7. Let's get Ruth back in here. Allie, go knock on the window for me.
Yeah.
Are there any questions in homework last night where the directions or even just the, like how to start it were weird? You can give me the numbers. Yeah, AJ.
There's a lot. There's a lot.
Is it like a section though? Where the directions were weird? Knowing how to approach. What do you got? 70-ish through, yes.
51 and 56 and everything after 70.
Okay, 51 and 56, ironically, actually 4.7 is going to help. So let me pause on that one just a little bit. Actually I'll write one of them on the board. You guys had 51 and 56, and then everything after 70?
Yeah, everything.
70 was saying put it in your calculator, look at it, hey, it's the same thing, that's all I gotta write. 73, 76 was just putting it in your calculator and looking at it and being like, ooh, the waves are changing. Like we talked about yesterday, being held in, the waves were being held in. That's all you have to say after a sketch. 77 and 80 is at the end of almost. You were graphing and talking about it. So all the ones in the 70s were basically like graph it and just see how by multiplying or dividing trig changes. So it's not something to memorize, it's not something that you would have to like do off the top of your head. It's just trying to basically show you that trig, sine and cosine do make waves, but when we put other things in, those waves won't always be the sinusoids we've been graphing. If you multiply by x, it's gonna like kind of be held in. If you divide by x, all of those are going to change, the heights of the waves change how they behave. So you don't have to memorize what those 70s are. If you're using your calculator, were you able to get it into your calculator, like to get a picture?
I didn't know where to start.
The y equals menu is where you want to start. And then you want to type in the functions, like e to the is the little second e button. And like type in e to the, and then you can actually type in negative x squared over 2 times sine of x, really standard radian mode. Look at it. Sketch it and be like, hey, the waves are changing heights. Does that make sense? So all of those ones are basically, hey, the waves are changing heights. Cool. What did that? I don't know. The math stuff they put in the functions. Okay. The waves are changing heights. And then in number 84 was like a word problem. That could have been a little messy unless you thought of opposite, adjacent, hypotenuse. It was really just solving a triangle at the beginning of chapter 4. 90 was the one we just went over. You're right. That was weird, so that's why I went ahead and did all of 90. So guys, in the 70s when it said graph it and look at it, it was just showing you waves change heights, math equations when they're being applied. If you're actually trying to show a wave, you guys know, drop a pebble in a pond. What's going to happen to the pond after time? Ripple. It's gonna, right? It's going to ripple, but then it's going to calm down. So in order to do that, we'd have to have harder expressions than what you're doing. They're just saying there's harder stuff out there. If you need it, you'll see it, but at least you'll know the sign. Ooh, there's a wave somehow. Does that kind of make sense? All right, kiddos. Number 51 and 56 was weird. Were weird. Well, 51 and 56.
I knocked on the window.
You think you'll get it, Ruth?
Yeah, please.
Hey, you stole my job.
No. She was supposed to be listening. Just go make sure. 51 and 56. I'm just going to write them down real fast because they were both weird. AJ, you were totally right on these ones. The other ones were like new and different also. But these ones were like way out there. Because both of 51 and 56 gave you a trig. 51 gave you cotangent with an equals. And 56 gave you cosecant with an equals. Now in this section they did tell you that you could use your graphing calculator. Or they said you could use a graph to solve. They said only look in between negative 2 pi and 2 pi. The first one said negative root 3 over 3. The second one did 2 root 3 over 3. Positive? Negative. Negative. Thank you. To be honest, I think the very worst way to solve this problem is with a graph. Now, they told you to use a graph because you didn't know any other way. My hope is that after we get through starting 4.7 today, is that you can at least have an idea as to what these questions are asking and how. So here, okay. In section 4.7, we're going to say, wait a minute, what are we going to do if they give us a trig and they give us a number? And they say, when does this happen? But one more time, in the directions they said x is in between negative 2 pi and 2 pi. X is in between negative 2 pi and 2 pi. So wait a minute, kiddos, if the x's have pi's, I'm actually introducing 4.7, that's why I had you come here. These were two problems they got stuck on in homework a bit. And these are the problems, the types of problems section 4.7 answers. Guys, negative 2 pi and 2 pi, what are those things that are measured in radians again? What are they called? Calzone was a way of remembering, that's true. But what are radians measuring? What are those variables, those quantities, those numbers? What are they representative of?
W. Pi.
Those are examples. Pi over 3, pi over 6, 2 pi, pi, 3 pi over 2. They're examples. What's the whole category? Who are those guys?
Radians.
Pi. Yeah, and degrees and radians both measure what?
Angles.
There we go. Angles. Okay.
More than a minute.
Thank you, Drew.
We're supposed to be finding angles. In both of these problems, we're supposed to be finding angles, but wait. So, who are these guys? If angles are what goes into a trig, sine of pi over 3, cosine of 150 degrees, tangent of 37 degrees, cosecant of 5 pi over 6. What goes into trigger angles? What comes out? Who are these guys? I know they're numbers, but like the category. What comes out of trig? What sign equals 1/2 at
The product.
pi over 6? If they are values, they're usually fractions, or they can always be written as fractions, and those fractions have meanings when looking at right triangles. Ratios of sides. Who's this guy? Well, guys, who's cotangent? Cow. Cotangent. Cow. Who is this guy?
Opposite of.
Careful. Cow.
Adjacent over. Cow.
So the cotangent is the adjacent over the opposite. How about cho? Who's this guy?
I thought you were opposite.
Section 4.7 says they're giving us the ratios and they're asking for the angles. Isn't that backwards what we've done in the unit circle like all year? Because the unit circle all year, didn't we work super hard on you guys knowing that 5 pi over 6 was in what quadrant? Third quadrant.
Get that article, man.
This angle.
Oh, Lord.
So when they ask you for sine of 5 pi over 6, and whether you memorized it with the unit circle or with the geometry triangles or with the little and lot. Either way, if you had gotten 1/2 as your answer, I gave you the angle and you were telling me. Ultimately, in some ways, the ratio of the sides. I gave you this, you gave me that. Now you were memorizing it to be able to go fast, but that's what was going on. Section 4.7 says, nah, we're going backwards. So what if I was to, as you guys get ready, notes open, get ready to start. Look up at the board though, get your notes open, pencil out. But instead of saying sine of 5 pi over 6 equals who or what, and you guys trying to find whether you memorize, whether you plug into your calculator, or whether there's a triangle. Pause, eyes on me. I know, you're getting ready to take notes. I know, pause, eyes on me. Allie, Jordan. Up until this point, I gave you the angle, you figured out the ratio, but now all of a sudden, I'm going to give you a ratio, and you're going to find for me the angle. Who knows the unit circle so well they can go back?
Isn't it?
No.
45.
Yeah.
Yeah, no, first one, because it's the first one, because it's.
Oh my
Okay.
4.7 says you gotta know so well you go backwards. Here we go.
No, I can't do that.
Here we go. This entire first page is building up to how to choose what answers to give. However, sadly, this whole first page isn't telling us how to go backwards necessarily. That's what I just did. What this whole page is doing is, where are you even allowed to legally be looking? For instance, if you were to open up your unit circle right now and look at it from section 4.2 or 3, 4.1, 4.2, anyway, if you were to look at it, there are 2 places that sine equals root 2 over 2. There technically is another place, and that's only in between negative 2 pi and 2 pi. Not even that. That's only in between 0 and 2 pi, 1 revolution of the unit circle. Does anybody know what other quadrant sine would also equal positive root 2 over 2? We're in the first quadrant right now. Second quadrant. All students, sine is positive in the second quadrant, which would also be at 135 or 3 pi over 4.
The unit circle.
No, it's hard though, right? Because we haven't been going backwards, we've been going forwards. Okay, kiddos, if you want to see something snazzy, you ready? Grab out your calculators real fast. Alright, go to degree mode, because we can see degrees that the calculator gives us. Radians, we can't see them, they give us funny decimals unless it's pi, we're stuck. So go to degrees, go to your home screen, no graphing. Go to your home screen, no graphing, degree mode. Ready?
Yes.
I want you to do second sine of root 2 over 2. Second sine of root 2 over 2 equals 45. But wait, there are 2 answers to that problem. The calculator's wrong?
Calculator's wrong.
Pause, there aren't just 2 answers to that question.
It's always wrong, that's why my answers are
Are
different.
you kidding?
Second sine of root 2 over 2.
I can trust your calculator.
Hold on, pause. You guys just did your calculator 45, right? Second sine of root 2 over 2, enter. If you're in degree mode, that would give you 45. That's the one that I had boxed, that's the one that Mari gave me, that's the correct, proper calculator answer. But if I was to graph, ready? If I was to graph sine, wouldn't that, okay, sine, hold on, that would go to 2 pi. This is what the homework was kind of having me do. Negative 2 pi. You go up to 1, down to negative 1. Sine starts in the middle, right? Can someone in a separate entry, can you plug in root 2 over 2 and give me a decimal? What is root 2 over 2 as a decimal? Like as a number, as a value?
0.7.
Okay. 0.7-ish?
It's 0.707.
Okay. 0.7, wouldn't that be around, I don't know, here-ish? Can't I put root 2 over 2, 0.7, a little bit below 1, is that true?
Yeah.
Where's it gonna hit the graph? Guess what? This is pi over 4, same thing as 45.
Oh my.
Where else is it gonna hit the graph? Here, which is 3 pi over 4, or 135. Guess where else is gonna hit the graph? Here, which would be, we'd have to go negative to get there. So it'd be negative 5 pi over 4. You have to turn negative to get there again to the other guy, which would be negative 7 pi over 4. Guys, here's the dilemma. How many times will sine truly equal that square root of 2 over 2?
Oh.
Infinitely many. Now, is it hitting every single place? No. It's hitting infinitely many times, but a limited infinity.
Wow.
Infinitely many times, but a limited infinity. There are different levels of infinity.
No.
All the points on the graph would be infinitely many points, but then there are going to be infinitely many points that hit as well. Just going to be smaller or less. The long story short, okay, if there are infinitely many answers to going backwards of sine with this problem I wrote on the board, which was sine of x equals root 2 over 2, well, I don't want you to write infinitely many answers all the time, and the calculator doesn't give infinitely many answers. So how many answers did the calculator give again? Just one. So the inverse sine function says, hey, you know what? Even though sine will hit every value that it possibly can equal infinitely many times, there's only one principal value. And that one principal value for sine is going to happen anywhere in between negative pi over 2 to pi over 2. We have to restrict sine and say, you know what? In order to get every single possible value of sine, we're going to have to cut the sine curve and say, no, no, no. We're only going to take answers between negative pi over 2 and pi over 2. Hold on, give me a second. We're going to cut the domain of sine down. The restriction is going to be only look between negative pi over 2 and pi over 2. And let me tell you why. Inverse is backwards, right? Inverse is undo. If I was to graph the inverse sine curve, everything would have to flip. And I would end up having something like this. The sine curve would have to reflect across the y equals x line like every inverse has up until this point this year. And when I flip it across the y equals x line, the problem is, kiddos, is this inverse sine, is it a function? No. So since the original sine would fail the horizontal line test, the inverse sine would fail the vertical line test, so if I'm trying to write a function of inverse sine, inverse, remember, it does not have that little -1 notation, f inverse of x, now it's sine inverse of x. If I'm trying to make an inverse sine function, I can't have it not being a function. So to make it a function, we cut it down and say, you know what, just like Mr. Calculator there, we're only going to be getting one answer, unless they ask us to use that one answer to find more. And so the inverse sine is going to actually only go, even though I could keep it going, it just wouldn't be a function anymore. The calculator couldn't give me just one answer. I'm going to have it only go in between negative, sorry, that's a positive. Positive pi over 2 to negative pi over 2, from -1 to 1. Which also poses a problem, because if sine can only go up to 1 and down to -1, then sine inverse can only have numbers coming into it. that are in between that negative 1 to 1. If I were to plug in, hey, let's try it. What's sine inverse of 2? Second sign. Second sign is sine inverse, not cosecant. No. Second sign. What's second sign of 2? Exactly. What's second sign of 1.1? What's second sign of 1.0000? I don't care. Put in some zeros and then a 1. But what's second sign of 1? Check it. But it was a good guess.
90.
Sine can go to 1, but it can't go past.
Oh,
And if I was to go to negative 1, sine can go to negative 1, but it can't go past. So, sine inverse only works in between negative 1 and 1 for values in between negative 1 and 1. And it will only pop out angles in between negative pi over 2 to pi over 2. Not saying that you couldn't look at your unit circle and find more, or like spin around and get some more. It's just saying there's only one, what we would call principal value. Now, let's talk about this guy. Sine inverse. There are two different ways of writing it. If he's a function, if you've restricted him, we can say f of x, function notation, is equal to either sine inverse of x. You guys say that real quick? Sine inverse of x. What do I not want you saying?
Inverse sine.
Don't say sine to the power. It's not to the power. Don't say reciprocal. It's not. Don't say cosecant. It's not. It's sine what?
Inverse.
Good. But there is another way of saying it. You guys know when you're like typing something real quick, how easy is it to like put in a superscript? Yeah, exactly. You have to go like find where the superscript thingy is. It's like up in the formatting of the text. So there is another way. And I think it's because superscript would be for the little negative 1. There is another way of writing sine inverse, and well, this is just my own little like, well, this would make typing easier if you were ever to type it. Arc sine. Arc sine. You can think arc. Well, I was thinking more like arcs in a circle, like the measurement around an angle, like an arc length. You can think of arc as in like, oh, hey, we're trying to find the angle that. All right. If you want to try to think of a way that Noah's Ark can help you remember this, you can. But anyway, arc sine is the exact same thing, and you can write this one without having to do a superscript. Without having to do an exponent. That's my way of saying it's easier, but there are two different notations. Focus. Every single trig function could be written as an inverse, cosine inverse, tangent inverse, cosecant inverse, secant inverse, but every single trig could also be written arc cosine, arc sine, arc tangent, arc cotangent, two different ways of saying the same thing. Okay, if and only if sine of y equals x. So ready? You guys can see a few things. I'm going to go ahead and underline in red. If you want to color code, that's not a bad idea. I'm going to underline all the x's in red. For trig, I'm going to underline all the x's in red. For trig, what goes in to an inverse? What goes into an inverse corresponds to what goes out of a trig. And all of those are angles. What goes into the inverse? Whoa, I did that backwards. Silly me. I know, right? Look at the board. It's okay.
what's going on.
It's okay. We're fine.
How am I supposed to learn?
Trial and error. Sometimes it's the way.
Buzz,
Allie, help me out. Do you remember?
Yeah.
SOHCAHTOA, what comes out of sine?
Wait.
Yep.
It's all the way here. Can you repeat that?
What comes out of the sine?
SOHCAHTOA.
SOHCAHTOA.
Opposite over hypotenuse.
Exactly. What comes out of a sine? SOHCAHTOA, opposite over hypotenuse. Or what goes into inverse? Those are ratios. And Jackie had this one, I think, when we were asking you.
So proud.
Ratios of sides. Okay.
Thank you, Mike.
So backwards. What goes into the inverse is what comes out of the trig, which are ratios of sides. And then the other thing we have to label is what comes, let's go green. What goes in to a trig is what comes out of the inverse. what goes into the trig is what comes out.
That's a lot of lines.
That's good one.
Arrows.
It's just lines too. It's a line.
Hence why I color code. What goes in to the trig is what comes out of the inverse. I didn't like this arrow, I should have done this one. There we go. Put your angles. Okay. One more time. Is sine inverse 1 over sine or cosecant?
No.
And I'm going to say a big fat no.
He's a little upset about that.
No.
That's a lot of
What does that kill?
I don't know, we should make it happen.
We should say
Okay. Now kiddos,
oh my god.
Okay.
What did you
Is
say?
yogurt real good?
if you,
Is yogurt real good?
well, Yogurtville is a place.
Oh.
No.
The yogurt in Yogurtville is usually,
Darn it.
it's usually Chobani.
Beck is wearing one.
It's like
Okay.
Manchester.
I'm more of just a fan of Yogurtville, I'm not really like
Are all
it.
the
I love
teachers wearing
French
that?
cheese.
I know, because Miss Reagan's mentioned. Because a lot of teachers are wearing.
If you want to know the secret of Yogurtville, you have to ask Mr. Strike or Mrs. Christensen.
He won't tell me.
Or,
Wait, what's the secret?
You can tell me.
okay, arc sine of
Secret?
-1/2.
Why is
That's
I blame
like
Mr. Strike.
So Mr. Strike me merch.
No, you.
Kiddos, calculators. Calculators, we'll start here, because we haven't gone backwards a lot. Calculators, but if you know the integral so well to go backwards, Mario was doing this a second ago, maybe you can try to beat the calculator.
I got this.
Don't say out loud what you do, but if you want, arc sine, it's the same thing as second sine of -1/2. Don't tell me what you get. Second sine of -1/2. No, I did not do this before class, I memorized it. Second sine of -1/2. I got this.
Okay.
For all of these, don't tell me. All of these, the answers are only allowed to go between -pi/2 and pi/2, which you guys are in degrees, which would be the same thing as only between -90 and 90. Anything that you plug in second sine will always get you something in between -90 to 90, unless it's an error. Question. Is the proper answer in degrees to letter A going to be -30 degrees?
Yes.
Or -pi/6?
Mm.
How did I get that without having the calculator?
Mental math.
You could do cheater chart. Sine is going to be 1/2, 1, 2, 3 at 30 degrees, but this is negative, so -30 degrees.
Hey.
Or
Allie, just silence.
I could have thought about my unit circle, and I could have thought of, wait a minute, in between -90 to 90, in the fourth quadrant, sine is negative, and the y is going to be -1/2 at -pi/6 or -30. So when I come to this one, you guys want to try without your calculator? Oh, how'd you know it though? First quadrant, it had to be, it's a positive. If you only had -pi/2 to pi/2, -90 to 90. If you're only looking at these angles to those angles, it couldn't be quadrant 4. Sine is negative, so quadrant 1, and when is sine 1, 2, 3? When is sine root 3 over 2? 60.
60.
60 or pi/6 would be the proper one. So, undo. Did you guys check in your calculator? Were you right?
Yeah.
60 degrees or pi/3. Okay, cool. 2. Oh, we have to use our calculator. 2 is not in the unit circle. I have 1/2 root 2 over 2 root 3 over 2, 1 or 0. Sorry, 0 or 1. Okay, have to use our calculator because it's not in the unit circle. Wait, pause. What did we just talk about?
It's undefined.
Or less
It's
than.
undefined.
It can't be bigger than 1.
So it's undefined.
A ratio can't be bigger than 1. So if you plug it in, we know right now it's going to be error or DNE or does not exist. Or none. I don't care.
Yes.
None, DNE,
Does undefined count or is it just?
or undefined.
There we go.
All of them are fine.
Okay.
A little bit.
Yeah, dude, why is the AC turning on?
Pause!
One time
I know, right? Letter D, unit circle. No. 0.265, that's not unit circle. 1/2 root 2 over 2 root 3 over 2, no. Oh, it's error. No, it's not. It's it's less than 1. Okay, plug it in. What do we
Put it
got?
undefined, guys?
18.367 degrees.
Good.
Okay, Chris.
What's happening?
Thank you.
Now, can someone tell me another answer that is just as correct, and because they didn't tell me any particulars in the directions, you could technically use it? What's another answer that would be just as correct? I wish I knew.
3669.
No, you should probably
Wow.
round it. You should probably round it.
That was cheap.
You could do degrees, minutes, seconds. You could, okay, that's one way. You could make it degrees, minutes, seconds. Just as right, different form. What's another way to get a just as right answer, but a different form? Because they didn't tell you.
Radians.
Yeah, you could change to radian mode. Someone do that. Change to radian mode, type it in. They didn't tell you which one, so you could technically put either one and they both be right.
I over 11 places.
Ooh, how'd you get that? Did you divide by pi?
No, I divided 180.
Oh, okay. Nick is transforming the angle to be a radian, which is really impressive because I've never had anyone do that before.
Wow, good job.
But you could have, probably the easier way, since it already has a decimal in it, would probably be just to go ahead and throw it in radian mode.
My God.
So in radian mode, you get point.
0.26823.
Okay, so then 8.2 would round to 8.
Wait, what?
So, kiddos, in these ones, unless you look at the back of the book and look at the labels to them, you can technically answer in degrees or radians unless the directions say something different. Okay, degrees or radians, if they don't tell you which angle they want, well, you're like, hey, they're both the same thing. Okay, but pause. Degrees needs to have a degree mark. Radians, none. True?
Oh.
True. Okay, we got 2 more inverses. Don't worry. Starting today, finishing on Monday, but inverse cosine, inverse tangent, guys, a lot of things are the same. For instance, inverse cosine. For instance, inverse cosine, he also is going to go between -1 and 1 because he's like sine. He never goes beyond -1 and 1. Inverse cosine, similar to inverse sine, does need to be cut down, but he's not going to be able to be cut down in the same place because he's been shifted. So, when we think about cosine, which we're just going backwards with cosine values, we would start at the top.
Okay.
We would start at the top for cosine. So if we're trying to cut the cosine to be a piece that passes the horizontal line test, we can't choose from -pi/2 to pi/2. That's going to fail the horizontal line test. So instead, for cosine inverse, we're going to cut the exact same branch as sine, in some ways. The exact same branch as sine from the very top to the very bottom, but we can't choose on either side. We have to start at 0 and go to pi. If we went from before to after, we'd actually just have a repeat of the exact same positive values. We need to go between 0 and pi, because then when we go to reflect, let's see, 1, that's pi, it's going to be more like here. When we go to reflect cosine, he's going to have the same problem. He's going to fail the vertical line test. So if we're able to just cut part of him and only choose this piece, that will be the piece that we're going to use. That goes from -1 to +1, from 0 to pi. That's who we have to cut cosine inverse down to be. That's how we're going to have to cut cosine inverse down. So sine inverse was in between -pi/2 and pi/2. Cosine inverse is in between 0 and pi. And for those of you that do like visualizing, I know what that was, visualizing the unit circle, we're looking only in quadrants 1 and 2. For cosine inverse, we're looking for answers only in quadrants 1 and 2. For sine inverse, we're looking in positive quadrant 1 and negative quadrant 4.
Oh, there's one key.
And tangent inverse, let's go ahead and look at on Monday. But I am going to go ahead and show you. You can go ahead and pause for a second if you want. I'm going to have you guys filling out notes probably first thing Monday. We are going to be looking at cosine inverse, which means cosine backwards. which can also be written as arc cosine. We're going to be looking at tangent inverse, which is going to be tangent backwards, and arc tangent. And you might think we'd be doing all 6 trig functions. To be honest, we'll probably stick to sine inverse, cosine inverse, and tangent inverse, because they're the only 3 buttons we have in our calculator. Bye. Bye-bye. Catch up on Precalc. We have a quiz next week and a final one coming up. Catch up if you're behind.
I'm always.
Happy holidays.
How about Rob?
Did he hear what he said?
No, he said, you need to catch up.
Because those months you asked me, besides 51 and 56, they were just... Yeah, you were trying to understand why it was, when they were really just asking you to be like, hey, it can be like weirdly transformed to be this, but you don't have to know all the math as to why.
Okay.
Does that make sense? I think you were trying to understand all the math. When you start dividing, it just starts getting weird.
Yeah.
Yeah.